所以一样的，我们有些 organization 的部分的要讨论一下。首先第一件事情是，因为上学期我的部分，因为你们知道我的比较是没有讲义的部分嘛，所以大家要我写，就是大家要讲义，然后我给的好多 review 都比较慢一点。所以这学期我们就改了，我们就直接用录影。OK， 所以我们就每次上课就我的部分，至少我的部分我都会录影下来。OK， 然后所以我录影下来之后呢，我们回去就放在网站上，这样子就没有写讲义的问题了嘛，对不对？就你们有什么不记得了什么的，就可以直接去看录影带，然后你们可以多看几次，去回溯说我那时候上课讲的东西是怎么样。我想这对大家也都比较 efficient 比较节省时间。OK， 这第一个。然后第二个部分是上课的时间也是一样，我们要讨论一下。所以你们是比较 prefer 像上学期那样子分成礼拜三、礼拜四的下午上，还是说一次礼拜四上完？还是你们要回去讨论一下投票？我们这边有没有人有意见的，可以先发声一下。
就是我做一的话，礼拜三的3点半到5点，就是
有课是什么课？
那个统计。
OK， 这边还有谁修统计？应该不止你吧？对 ，OK， 所以你们都是3点到5点有课，统计会上。
对，3点半到5点。
OK， 那3点之前呢？这边有没有3点？礼拜三3点之前有课？好 ，OK， 好，那所以礼拜四，那如果我们就恢复到礼拜四上2堂，可以吗？哈，大家还暂时 OK。好，那我们就先暂时先恢复礼拜四上2堂，好。OK， 好，然后OK， 那我再跟恒宇讲。好，那个这学期我们会稍微再尝试一下，就是说用双语上课。OK， 所以我们会用英文跟中文这样夹杂上课。这边对英文上课有没有？我这样问好像，这边觉得英文上课没有什么问题的，举手。没有什么问题。OK， 好，那我大致上知道。OK， 所以但是没关系，我会英文跟中文夹杂。OK。All right, so let's begin. So this course is QFT2, essentially. So this is okay, and so for the census 2, we need to figure out what we actually know from QFT1. Okay, what do we actually know here? So So basically, I'm going to spend 30 minutes， 我大概花30分钟的时间，先跟你们讨论一下，你们从上学期里面，你们应该要学到什么东西，然后是我们这学期会继续延续的，从这个那个方向出发。OK， 那上学期你会学到什么呢？你会学到说，我们应该要知道说，我们 care 的 physical observable 是什么？对，因为这个非常重要。Obviously， 我讲非常重要，好像是废话的。但是因为这学期我们牵涉到的是讨论quantum correction。OK， 那 quantum correction 你要 properly 去理解 quantum correction 是什么的时候，你必须要从实验的角度去了解它。OK， 所以既然是从实验的角度去了解它的话，那你当然就必须要知道说，到底我们在实验上在两侧的这个东西是什么，这个 physical observable 是什么。那我们上学期已经讨论过，说你的 physical observable 主要有2类。第一个就是，或者你可以想象说我们在做的实验是什么，就是你有 scatter particle 进来，然后 scatter particle 进去，对不对？这就是，然后so there's 2 kinds of physical observable that we discussed last semester. So basically, one is the process, so how to describe a process where you have particles interacting and the particles going out. Okay. And this we've known that this is called the S matrix, which is something that we discussed last semester. And the other thing that we would like to know how to compute is some quantity, is in some, for example, in some medium. And then you would have operators sitting here, sitting at x1, another operator sitting at x2, and another operator sitting at x3. And then we would like to know what is the expectation value of these operators sitting at different points. Okay, so this is the correlation function. So in QFT1, we basically learn how to, in principle, compute this and this. So if I'm writing this down and you don't know how to compute it, then you need to take QFT1 again. Okay, but I mean, you don't need to know how to compute it, like every step of the way how to do it, but you should know that in principle, how these observables are computed in principle. Okay, and so this is really what was established in QFT1. Now, so let's just go, now since I don't want to be too harsh, so let me just give a brief review of how these variables are being computed. So basically in both cases, where here this is, the S matrix corresponds to some incoming state, so this is in state, and out state. So basically, again, this is also another expectation value between in state and out state. Okay, so that's essentially what we mean by the S matrix. So in both cases, we're computing an expectation value, right? So whenever you're computing an expectation value, what you need to do is you first need to identify what are the states, right? And second is how to compute the expectation value. But there's two things, okay? First is you need to identify what are the states. The second is to identify how to compute an expectation value. And that's what we did in last semester. Now, what is the state here? Okay, you might remember that in last semester we have a lot of discussion about the whole S matrix thing here, right? But we have relatively very few discussion about this here, right? About the correlation function. Right? I might just wrote down some general formulas for you, but we didn't really compute a lot of correlation functions in last semester. Why? It's very simple. It's because last semester we were mostly focusing, when discussing this, we were really, the reason that we focus on this more is because we were really focusing more on this, the idea of what the states are. And you'll see what I mean in a minute. But here, the state is trivial. The state is the vacuum. Okay, when we're discussing correlation functions, usually we're discussing a correlation function in a vacuum. Okay, of course, for more practical or in condensed matter systems, you might consider the correlation function in some non-trivial background. But generically, we're talking about correlation functions in a vacuum. Okay, and so there's not much state discussion here, and that's why last semester we didn't discuss a lot of correlation functions. Okay, that's why you only see this last semester and not much this. Because we're basically discussing states, okay? And now you might disagree with me because you think that, wait a minute, no, but last semester we learned fermions, right? We learned how to do Dirac spinners, we learned the Dirac equation, we learned the Klein-Gordon equation, right? Why do I say that we're just learning states? Well, I'm just, actually all the things that I've listed is just telling you what the states are. Okay, so let me just give a brief review of why this is true. So now we know what the physical observables are, and it basically consists of two important ingredients. One is the states, and two is how, well actually you know what expectation values are. So basically all you need to do is how to compute expectation. So last semester was all focusing on this. So what do I mean? So in the beginning of last semester, we know that the states, we often like to think of the simplest kind of state is one particle states. Right? And how do you classify one particle states? You classify it by little group. Right, which you should know, be very familiar by now, right? And we know the little group for, which is defined with respect to your momenta. So we have either the case where your momenta is massless, or the case where the momentum is massive, right? And we know that for momentum is massless, you would have what we call the helicity, and for momentum, for the momentum that is massless, the little group is U1. And for momentum that is massive, the little group is SU2. And for most of you who went to, some of you who went to my talk yesterday, you'll see a lot of SU2s in my talk yesterday, right? But essentially, it's just a massive little group. Everybody know what a little group is? 你都知道吗? Little group 是什么? No, the fact that little group is SU2, 你可以接受. Okay, good. So basically, when we say one particle state, what we mean is basically all the representations that are possible under these two symmetries, right? And so for here you will have 0, again, plus minus 1/2, plus minus 1, plus minus 3/2, and so on and so forth. And for SU2, you all know SU2 from quantum mechanics, right? You all know the representation of SU2. You label by L and Z, or J and JZ, or whichever you use. So basically we have, again, 0, and then we have the doublet, and then we have the spin 1, and then we have so on and so forth, right? Okay, so this will be the way that we label one particle states. Okay. Okay. Now, after labeling one particle states, we learned about fields in last semester, right? So fields is supposed to represent these one particle states, right? And so how do we do that? So basically, but before actually going into the explicit construction, let's just try to reconstruct this a little bit. So let's say we were trying to think about two particles coming in, and then two particles coming out. And let's say that we view our world as particle 2, 3, 4. Okay. So let's say these particles are part of what either as a massless or a massive, I don't care. It's just like some kind of particle. Okay, so now I want to describe this process. Okay, so what would I need to do? Now, first of all, we know from last semester this is quantum field theory. So you know that what you would like to do is to introduce a field, let's call it phi of x, where the field represents these particles. Right? Do you agree? 所以我们会想要说引进一个场在这个地方，这场是代表这些 particle， 对不对 ？OK。可是问题说这个场，我们写下这个场，用这个场来 represent 这个 particle 的时候，这 obviously 不是一个正确的事情。为什么？因为我们想要去描述这件事情的时候，这个场必须是要能够 freely propagate 进来。对不对？可是这个 phi of x 是不是一个 arbitrary 的 function？ 对不对？所以 naively 如果就写下这个场来代表这个 particle， 你们应该是觉得这 completely doesn't make any sense。虽然你们已经习惯了场论，虽然我现在是得故意再把你们习惯的东西，我还是要故意去给你们受一些质疑，放一些质疑进去，然后这样子你们会比较 appreciate 真的在发生什么事情。First of all， 当你说你在想说这一个 particle 是一个场的时候，这 in some sense it doesn't make any sense， 对不对？这是个 arbitrary function， 对不对？那这我们在描述一个东西 particle 进来，这一个 arbitrary function 怎么可以去描述 particle 进来？应该真正的描述 particle 进来的是什么东西？它是不是 somehow 应该是 exponential I p1x， 这才是一个 particle 进来的 form， 对不对？所以你们在写下一个场的时候，你们就应该觉得有点怪怪的。Fundamentally， 如果说你有这个 physical picture， 说你今天是要描述 particle 进来出去这一类很复杂的时候，我写下一个 field 的时候， 或许你们已经习惯了，所以说你们会觉得怎么样？但是说实在，你们退一步想，你会觉得这 completely doesn't make any sense 的，因为应该是这个 function 才 make sense 去描述 particle， 对吧？ So here what I was just trying to say is that, so we're used to thinking about particles as field, but if in a more physical sense, this should smell that there's something funny about this, because if we're writing down some function phi of x, this is some arbitrary function. Arbitrary function is just arbitrary, so it can be anything. But we know that if it's really a particle that is freely propagated, it should be exponential IPX, which is a plane one, right? So we're trying to describe this, and we're trying to use a field to describe this, but obviously the field is not the right thing. Okay, so this I need to explain what is the correct thing to do. Second of all, here we know that all the fields should interact at a point, right? So that means that interaction should look like something that looks like a bunch of fields sitting at the same point, right? But which point? Which point is this? It should be. This should happen at any point, right? These particles should be able to interact at any point, right? So, in order to solve these two problems, last semester we realized that we can solve these two problems by doing this. By using something that was familiar for you from classical mechanics, and that is to write a path integral. Okay? Now why does writing a path integral solves this? Because first of all, now this is a function of your fields. But you're integrating over a whole space-time. Right? You're integrating over the whole space-time. And so even though your interactions are local, but the point in which your interaction is occurring is over all space-time. Okay? Okay, so this, we're just writing it as in this form, solves this problem. Okay? 我现在有两个问题嘛，对不对？我现在第一个问题是我今天若想要用 field 来表示的时候，这个 field 是一个 arbitrary function， 我要 somehow 把它 relate 到一个 plane wave 才能描述一个 single particle， 这是第一个问题。第二个问题是我们知道我们的 interaction 都是应该是 local 的 interaction， 我们不会有超距的 interaction， 对吧？我们任何东西的 interaction 都是一个 local 的 interaction。那所以如果是一个 local 的 interaction， 就代表说你所有的 field interaction 都必须是在同一个点上，你只能写下，你要 somehow enforce 这件事情。可是同时这个点又不是 anything special， 对不对？因为我们这是罗恩兹别人世界，每人都可以做罗恩兹transform 到这边 transform 到那边，所以你应该没有任何的 special point， 对吧？所以你们就学了一个 special 的 formalism， 就是用所谓的 path integral 的 formalism。我们先 start out with 一个 field， 然后你继续有个 exponential， 你再 integrate over 这个 Lagrangian density 也是 dx 的事实嘛，这 dx 实际上就很重要，因为这就 solve 了所有，你要把就 solve 了这个问题。对不对？好，那你怎么 solve 这个问题？谁可以跟我讲？就是你们上学期学过，只是你们不是用这样子方式去想它的。你们怎么去 solve 这个问题？啊？Okay, what kind of function? Does every function look like exponential IPX? No, right? This is exponential IPX is a special function, right? This is a single particle. I'm not doing something like CP and then integrating them. I'm not doing this. I'm just saying this is a single particle coming in, right? So we need this function. But here, when you're trying to do something like this, we're integrating over all functions here, right? So this is obviously not that. So this solves this problem, but this doesn't solve this problem. So you all learned how to solve it last semester. What did you do to solve that problem? We're just talking about scalars here, right? So this should be very simple. How? That's about 5% the correct answer.
Introduce source.
No. This is a very simple thing. How did you solve that? How did you, I mean, this, again, so let me say this, and so the hint is already in the sentence, okay? You're integrating over all functions, right? All possible functions. But somehow you're able to focus on something that is just a plain way. You're able to localize on something that was a plain way. So what happened? How did you do that? You already did it. You just didn't know that that is the correct way of interpreting it.
I think the particle here is a state.
Okay.
Your integral is say is a function. So you have to. This is a different kind.
Okay. So what did you do in this integral from this integral? How would you get that? So let me put that question. How would you get that function out?
You have to do an operator acting on the state. Then here is the particle state.
That's not the okay. That's not precisely the correct answer, because then you're making things more complicated, because then you need to tell me what an operator is, right? How do you define your blah blah blah? So you're going to tell me that your operator is a thing on the vacuum that creates the plane wave, but that's not the answer. That's not the answer, right? You see what I'm saying? Right? You understand what I'm saying? You're saying I'm introducing an operator that hits on the vacuum that creates a plane wave. That doesn't answer. You see what I'm getting at, right?
Because that's the only mode which survive when you consider from infinity to the past to future.
But I mean, how did you do that here? And why is that true?
Because
okay, so
all the other thing will be averaged out, or
okay, so I think it's time to introduce the answer. The answer is you had a 1 over h bar here. This is very important. So what happens when you have a 1 over h bar? Well, having a 1 over h bar doesn't really do anything, but what is important is that h bar is much smaller than 1, right? So why does h bar much smaller than 1 actually creates that state? Why? Yeah. So actually I'm giving you the answer. Can you extrapolate from this? It's because when h bar is much smaller than 1, this integral has a maximal contribution from the saddle point, right? Right? When h bar is much smaller than 1, you have a contribution to the saddle point. And what is that contribution coming from? It's coming from the equation of motion. Right? The dominant contribution is from the equation of motion, which you know what it is. Right? Because you have an h bar here, that means it's reasonable to first consider the saddle point of this equation, right? And for a scalar theory, what is the saddle point? For scalar theory, the saddle point is box phi equals 0, right? And therefore, you have this solution, right? The plane wave is a solution to box phi equals 0, or right? You know why, right? Because box phi acting on that is just equals to p squared acting on phi, which is 0, because p squared is 0 for masses. For massive, you can do the same thing. Okay, so think about it. So the fact that you have a particle coming in, even though you're used to thinking about now you can just introduce field to represent the particle, but the very fact that you have this notion of a particle means that even when you're using a field, you need this h bar here. Okay, otherwise there's no reason why your function should look like a plane wave. Right? The fact that your function should look like a plane wave means that you need an h bar here. Or in other words, it means that you need a classical limit. Right? Because giving you an h bar defines what the classical limit of this thing is. If I didn't have an h bar, this doesn't mean anything. It is just you're just forced to sum over all possible fluctuations, and there's no notion of particle scattering and so on and so forth. Okay, so even though in any quantum field theory textbook, you always get used to setting h bar equals c equals 1, right? We always do this, right? H bar, we don't count the h bar, but you always have to keep track. The reason that you're doing quantum is because you have this h bar here, because h bar tells you what is quantum, what isn't quantum. And so I want to so in this first part of the first lecture of this entire course in the second semester, I want to make a very big emphasis on where the h bar is at, because that's really where what the physics is, what you're really doing physically. Okay. So in last semester you learned about how to do equations of motion from your Lagrangian and do computations. But really, you have to keep in mind that the reason that you're able to do equation motion is because of this h bar, and because of the very fact that h bar is very small, much smaller than 1. Okay? Okay. Now, so now that you've learned that, okay, the h bar is much smaller than 1, and the equation, so basically what the equation of motion is doing is, the first thing is telling you what the states are. Right? What the states are, the equation of motion, for example, for whatever satisfied box phi equals 0, and for example, for fermion, you would say it satisfies psi bar equals 0, and for example, for a vector, you would say that it satisfies f mu nu is 0. Right? And these are the 3 important equations that you learned last semester. Right? The Dirac equation, the gauge introduced field strength that we introduced solution. The field strength should be conserved, and then you have the Klein-Gordon equation. Of course, these can all become massive. So the massive case of the box minus m squared, phi equals 0, and this will be psi equals 0. And there's an issue with massive vectors, so we usually just write down them as masses. But you've been learning these equations, right? And how to derive this from the Lagrangian, right? From the equation of motion. We've learned this last semester, right? Okay? But you see that these are just telling you what the states are. Right? These are just telling you how the states emerge from this path integral, right? You have the path integral, you have an h bar that is much smaller than 1, and then that means that you're allowed to look at just the equation of motion. And then once you look at the equation of motions, you see that these are the equations of motion. And then these tells you what the states are. Okay, and now we can match, right? Because, for example, these are just fine. This is not really a constraint, but let's consider here the fermion. Okay, so for example, we know that a fermion, for a massive fermion, this form as a representation of SU2, and for the formulation of a massive fermion, the SU2 should have +1/2 and -1/2 states, which is complex, right? So there's 2 complex degrees of freedom, right? There's 2 complex degrees of freedom. Now, how many degrees of freedom do you have in a Dirac fermion? A Dirac spinner. How many degrees of freedom is inside? Who can tell me? Good. Complex or real? Good. There's 4 complex degrees of freedom here, right? Okay, but this is an equation, right? And this equation is actually a matrix equation. It's a 4x4 matrix equation, right? So it's actually, this equation relates 2 of the complex degree of freedom to the other 2. Okay, so this equation reduces your degree of freedom down to 2, which is precisely what you would expect from SU2, because it has 2 degrees of freedom. Okay, so that's why in the previous lecture in last semester, when I started the whole lecture, I started by first telling you